Welcome back, everyone, to the second lesson of the week. This is a continuation of section 3.9. So we have more problems to do in problem type 1. This is expanding or contracting geometric objects, as you can see. So this is a continuation of the problem type that we were doing before, just with a little bit more fun, you know. All right. So we have the length of a rectangle is decreasing at a rate of 1 centimeter per second, and its width is decreasing at 2 centimeters per second. When the length of the rectangle is 30 centimeters and the width is 40 centimeters, how fast is the area of the rectangle decreasing? All right, so this is a really weird question. You have a rectangle. And we know it's a rectangle, not just because it says it's a rectangle, that's what's underlined, but we know that the length and width are different at the moment, and we know they're also changing at different rates, all right? The length of a rectangle is decreasing at 1 centimeter a second. The width of a rectangle is decreasing at 2 centimeters a second, all right? And so just for continuity's sake, I'm going to do some underlining here. The length is changing at 1 centimeter a second, and it's decreasing. That's important. So I'm going to put a little negative here. To remind us. All right. And its width is decreasing. So let's use a different color here. That's not going to show up well. The width is decreasing at a rate of 2 centimeters a second. And again, I'll put a little negative sign there to remind us it's decreasing. All right. When the length of the rectangle is 30 centimeters. All right, so we got the length of the rectangle. We'll choose a color kind of like red, say orange. When the length of the rectangle, so the length is 30 centimeters. All right, and that's positive, of course. We're not having negative rectangles here. And let's choose another cool color like green for the width. And the width is 40 centimeters at a certain moment in time. All right. So we have blue and green representing the width. We have red, and it might look like yellow to you, but that's orange on my screen, representing the length. All right, so how fast is the area of the rectangle decreasing? Now we need to talk about area of a rectangle, all right? So area of a rectangle, we think that it's going to be decreasing, and that would make sense because all the change is in the negative direction. So wouldn't it make sense that the area itself is also decreasing? And that is in fact true. All right, so we are first tasked with representing the area of the rectangle and differentiating it with respect to time. All right? Area is equal to length times width. All right, that's basic. All right, so now we take a derivative, and we need to remember to use chain rule, right? Length times width, we would say dA dt is equal to L dW dt plus W dL dt, okay? It's important we remember a product rule, all right? It's important that we remember product rule, all right? So we have product rule here. We are multiplying L by W. I might have said chain rule before. I meant product rule, okay? So we have product rule here. And what's tempting is to say dA dt is equal to dL dt times dW dt, but that is not true. It will get you the wrong answer. That is not how we know how to take derivatives. All right, cool. So now we're going to use related rates to solve our problem. And I want to hand this off to you. I want you to take a second. I want you to do some substitution. Use my color-coded substitution tips for some help here. And you can probably substitute, do some arithmetic, figure it out. Take a second to do that. All right, and unpause the video when you're done. All right, I will assume you have given this problem a go. Let's look at the solution. All right. So we're going to use our related rates to solve the problem. All right, so dA dt is equal to L dW dt plus W dL dt. All right, so we're taking our original equation and we got it right here. All right, so now we're going to substitute. We say dA dt, that's what we want to find, right? is equal to 30 centimeters times negative 2 centimeters a second. All right, where did we get those? Well, we're talking about L times dw dt. The length is 30 centimeters, and the width is changing at a rate of 2 centimeters per second in the negative direction, so the width is getting smaller. Plus 40 centimeters times negative 1 centimeters a second. Again, just substitution. W is equal to 40 centimeters at the moment of interest and negative 1 centimeters a second. There we go, right? So first we take our derivative, then we substitute. We never substitute before we take a derivative. That doesn't make sense. We need all the characters here, and then we can take a derivative, okay? Cool. All right. dA dt then, after a bunch of arithmetic, is negative 100 centimeters squared per second. So negative 100 centimeters squared per second is the rate of change of the area of the rectangle with respect to time. All right, so there you go. At that moment, not at every instant, but at that moment, we are decreasing at 100 square centimeters per second. Cool. All right, let's move on to the next problem. The radius of a sphere, r, increases at a rate of 10 centimeters per second. What is the rate of increase of its surface area when r equals 30 centimeters? All right, so now we're dealing with a sphere, okay? So we have a rate of increase of a radius here, the radius r, increases at a rate of 10 centimeters a second. All right. All right. And now we have something interesting going on here. We have a radius increases at a certain rate, but the radius also, at the moment that we're concerned about, has a length of 30 centimeters. Okay, so we're talking about the radius here, but we're also talking about a sphere, and we're talking about its surface area. All right. So we're talking about a sphere, right? So we're talking about a sphere here, and we're talking about its surface area. All right. That was yellow highlighter-ish color. Maybe that showed up, maybe it didn't. All right. So we have a sphere surface area, and we have a radius that is changing at that rate and has that length. All right. So we're going to represent the surface area of the sphere and differentiate with respect to time. All right. So let's get going on this, but not before I give you an opportunity to set up the problem. You may see a little bit going down here. Try it for yourselves. If you forget, the surface area of a sphere is 4 pi r squared. All right, you can look at the back of my room. You can probably see a formula. There you go. Now you can turn around, Xander. All right, back to your work. All right, cool. Let's get to work. Give it a second. See if you can represent the surface area and differentiate with respect to t. All right. I will assume you've given the problem a go. Let's look at the answer, right? All right. So we have a is equal to 4 pi r squared, and dA dt is equal to 8 pi r squared dr dt. And I see that I have the entire problem right here. Woohoo. All right, so I can just get rid of that because that is related to the second part. So I have dA dt is equal to 8 pi r dr dt. All right, so we found the formula here. Now all we have to do is substitute for number 2. So you can take some notes on how we would do part 2. Use related rates to solve the problem. What's the problem? We're trying to find a rate of increase of surface area. So let's plug and chug from here. We find dA dt, 8 pi r squared dr dt, which means that we plug some stuff in. Radius at the moment of concern is 30 centimeters. All right. And dr dt is equal to 10 centimeters per second. All right, so that would, the units would be centimeters squared per second, which makes sense. This is a change of area with respect to time. And we have 8 times 30 is 240 times 10 is 2400. Don't forget about the pi. There we are. Good. Just like Christmas dinner, it's not the same without the pi. Although you're not thinking about Christmas at all. This is February. I'm making this 2 days after Christmas, so I'm still thinking about Christmas. Oh, wow. All right. Probably thinking about Valentine's Day at this point. Ooh. All right, so next problem type. All right, I warned you about these here. I warned you about these. So we have problem type number 2. We got the water in the tank. A cylindrical tank. All right, that's a tank shaped like a cylinder, of course. A cylindrical tank, we're going to use red, good, with radius 5 meters is being filled with water at a rate of 3 meters cubed per minute. We're going to assume the tank is situated on its base. All right, so just so you know what I'm talking about here, situating it on its base would look like this. We have our cylinder. Let's draw the cylinder right here. Dot, dot, dot in the background. All right, cool. So here's our cylinder. It's situated on its base. That guy right there. All right, so if it were not situated on this base, it would look a little bit like this, okay? It would look kind of like this. And that is difficult, okay? That's really tough. We're not doing that. We're doing this guy. All right, cool. So hope you're feeling good about that. I'll clear the screen. Let's hop to it. Okay, so how fast is the height of the water increasing? So we're trying to find the rate at which the water is increasing in height. Okay, so let's do a little bit of underlining before we get started. So we have a radius here, and the radius is going to be 5 meters. All right. Now, very important. This radius does not change. All right. I'm going to draw a cylinder again. Right. Now, this is not a perfect cylinder because I'm not a perfect person. However, we can see that this cylinder has a constant radius. The width of the cylinder, because it's a cylinder, is not going to change, okay? So that means that half of the width is also not going to change. So the radius is going to stay constant, which means, and this is very important, dr dt equals 0, all right? 0 what? Well, it doesn't matter. It's nothing, all right? So dr dt is going to be equal to 0. That's a big deal, and we'll talk about that later. That makes this problem possible, okay? That makes this problem possible. All right? Cool. All right, so represent the volume of the cylinder and differentiate with respect to t. That's the first thing we're going to do, and since you can see a lot of it, I'm just going to scroll down and show you. All right, the volume of a cylinder is pi r squared h. All right, so we have pi r squared is the area of the circular base times the height. All right, it's as if we are pushing a circle into 3 dimensions by multiplying it by the height. Convenient, no? All right, so now we need to implicitly differentiate. Ooh, that was tough. All right, stop laughing, Caitlin. All right, so dv dt is equal to pi r squared dh dt plus h times 2 pi r dr dt. All right, again, we need to remember product rule. I am grouping this in the following way. Here is 1, and here is 2. All right, so I have 1 d2, that's my first part, plus 2 d1. That's my second part. All right, you can check that if you would like, okay? So 1d2 plus 2d1, need to remember product rule, okay? That is gonna get you, all right? It's very tempting. It might happen, all right? I'm not saying it's gonna happen, but it might happen. You get to a problem like this, you say dv dt is equal to 2 pi r dr dt times dh dt. That is convenient. It's also completely false. All right, so that will not get you the right answer. You need to remember product rule. Historically, one of the biggest problems for calculus students is they see a situation like this and they have the gist of how the problem goes and they forget product rule. That has haunted my calc students over the years. You can do it. You can remember product rule, all right? Samuel, you can remember product rule. Xander, Caitlin, Jacob, you can remember product rule. All right? Cool. All right, now we're going to use our related rates to solve this problem. Now, I'm going to walk you through this one. I would love to hand this off to you, but there's a detail that I absolutely must hit. All right. And just to make sure that you don't get off on the wrong foot and get royally confused, I'm going to walk you through this one. Okay. So here we go. We're going to use our related rates to solve the problem. dv dt is equal to pi r squared dh dt plus h times 2 pi r dr dt. All right, so that is the formula that we found here. All right, cool. So that's our dv dt formula. So now we're going to substitute. And I want you to pay special attention to the substitution. We know from the problem that the cylindrical tank is being filled with water at a rate of 3 cubic meters per minute. All right, 3 cubic meters per minute, that is an expression of volume. All right, so the rate of change of volume with respect to time is 3 cubic meters per minute. Okay, now the radius at the instant, all right? The derivative is the realm of the instant. We're working in the instantaneous world, all right? So at the instant, we have a radius of 5 meters, all right? So we have a radius of 5 meters, not just then, but always, okay? And dH/dt, we don't know what that is. We need to find what dH/dt is. All right, so how fast is the height of the water increasing? That is dH/dt, all right? Plus 2 pi h, all right? So we don't know the height at the moment. That's a bummer. We know the radius, and we also know the rate at which the radius is changing, okay? So I do not know how high the water is, but that doesn't matter. The reason that doesn't matter is because my radius is not changing. All right? That is uber important. Also, if you forgot to do product rule in step 1, you would get 3 equals 0. That's obviously false. So sometimes the problem will tell you in no uncertain terms that you did something wrong. Okay, so if you ever get a false statement, you probably did something wrong in your derivative. Anyway, this whole part right here that I'm highlighting, all right, this whole part, this section, it's 0. That is so convenient because you don't know how high the water is. There is no indication in this problem of how high the water is, right? So you have your radius is of that length. You have the height of the water increasing. That's dH/dt. That's not h, okay? So you're given no information about the height, but it doesn't even matter. Isn't that great? So I told you before that the rate of change of the radius being 0 is going to make this problem possible because you don't know the height, but the height doesn't matter because the radius isn't changing. Yay, product rule. All right, cool. Next step, we eliminate all that I highlighted and now unhighlighted, and I have 3 meters cubed per minute. Whoops, there we go. 3 meters cubed per minute is equal to pi times 5 meters squared dH/dt, and it's just a little bit of squaring and a little bit of division. And we have 3 over 25 pi, all right? So that is a very small number. Meters per minute is equal to the change in height with respect to time, all right? So this is a small change of volume that will result in a very small change of height. All right, and that is for every instant. And it makes sense. If you have a cylindrical bottle and you know that the volume is increasing at a constant rate, the height's also going to be increasing at a constant rate, no matter how high or low the water is, assuming it's a perfect cylinder. All right, cool. Now, let's move on to the next problem. This is the last problem for today's lesson, and then I'll turn you loose on the homework again. Now, this problem, just going to warn you, is fun. My definition. This problem is an adventure. Whew. Alrighty. So, a water tank has the shape of an inverted circular cone. Why? To irritate calc students. Moving on. With a base radius of 2 meters and a height of 4 meters. Yes, Samuel, that is the reason. Okay? Cool. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay? Whoa. All right. Now, this problem, I warned you, this is the wild one here. And there's a problem very similar to this in your homework, so you're going to be grateful that we did this one. It's going to help you a lot on your homework. All right, so we're going to take out our pen here. We got some work to do. Okay, so you got our water tank in an inverted circular cone. Now, inverted circular cone, what that means is we got a cone. Normally, cones point up for whatever reason. Now it's pointing down. It's like an arrow pointing down, right? With a base radius of 2 meters, all right? So the base, that's the flat part, all right? Not the curved part, all right? So we have the flat part. All right, so the base radius is 2 meters, all right? Now, does that say anything about the watery region right here? No, that says something about our vessel, all right? So we have 2 meters. All right, so let me just sketch that. Got 2 meters. All right, good. All right, that has nothing to do with the watery region. That has everything to do with that. Okay, so the height then is 4 meters. Right, so I'm going to use this pinkish color right here, and I'm going to make a label. It's this big guy right there. All right, now the height is going to be 4 meters. All right, that's the whole height. That's from top to bottom here. I realize my bracket could have gone longer. Stop making fun of it. All right, so it's short, just like me. All right, so we have nothing again about the height of the water, but we know about the dimensions of our vessel. All right, so if water is being pumped into the tank at a rate of 2 meters cubed per minute. All right, check this out. I'm going to draw water. All right, so this is an arrow of water. This is like water bending right here. It's blue and it's an arrow. It's water. All right, cool. So water is going into the tank at 2 cubic meters per minute. All right, cool. 2 cubic meters a minute. Water's going in. Like that water? I don't care. All right, so find the rate at which the water level is rising. All right, so what's that? The water level is rising. Now, the water level is a measurement of height, okay? So the water level is a measurement of height. And I'm going to do this in the purple here. I hope this is not confusing. All right, so the water level, we want to say, okay, this here is the water level. This is the level of the water. All right, that's H. And we want to find, all right, dH dt. All right, we need to find dH dt. When what? In the instant, all right, we're going to need to get a derivative, right? We got to find height with respect to time, volume with respect to time, yeah, all that stuff. All right, but when H is equal to 3 specifically, H is equal to 3 specifically at the moment, that's when we need to find the rate of change of the height with respect to time. Judging by the amount of sketching I've done on this figure, you can tell that this problem's a little bit tricky, right? Cool. So I am going to keep my little sketches up here. Hopefully Screencastify will cooperate. It's usually good with this kind of thing, but we shall see. All right. Oh, it's doing great. Good. So let's get started. The volume is equal to 1/3 pi r squared h. All right. That is the formula for a volume. Yes, that is 1/3 of the volume of a cylinder. All right. There's a fascinating proof for that. Not going to get into that, but that is one that you probably learned in geometry way back in the day when math was easy. All right, volume equals 1/3 pi r squared h. Neat. All right, so dV dt is equal to product rule again. Do not forget product rule. Write down that derivative, all right? Again, I'll show you how I set it up. So I'm going to call this part 1, and I'm going to call this part 2, okay? So we have 1 d2 plus 2 d1, okay? I'm going to get into a more seeable color now. All right, cool. So as you can see, that's a lot of variables, all right? To count, just on the right side, I see 4 variables, which we know that 4 equals infinity. So basically, there is an infinite number of variables on the right-hand side, all right? Your substitute teacher does not know about that reference. Most likely, you'll have to explain that one to her. All right, but in order to find dv/dt, we have 4 variables. Let's talk about what we don't know. Pardon my dog if you hear him bark. All right. Oh, there he is. All right, I'm going to move to a better location here. All right. So we are moving through the Declarico house right now. All right. So let's talk about what we don't know. Let's talk about what we don't know. So what we don't know is what we don't know is anything about the radius at the moment. We don't know the change of, we want to find the change of height. We know the height at the moment, but again, the radius of the moment is rather obscure. So what's going on? How on earth are we going to find all these variables? Well, this problem involves a little trick. And it's a trick that you learn in geometry. The trick is related rates. Oops, that's what this lesson is. The trick is similarity. All right? We're dealing with similar triangles, right? So I'm going to draw you a picture of this scenario. I'm going to draw a picture of this scenario based on the picture above. So let's get the pen out here. This is just going to be the right-hand side of my figure. All right? So this triangle right here, that's going to be what I'm drawing down here. So this is my vessel, the right-hand side of my vessel, cross-section of it, if you will. All right? And here is my water. All right? We'll make it blue. All right, so that's how high my water is, and we can shade it in, you know. All right, so there is my vessel and the water therein. So the height of my vessel is 4, as you recall. And it's in meters, of course. So I'll just put a little 4 meters right there. All right, and we have a radius of 2 meters. Now, what about the water? Well, the water is unknown. The water has a height of h and a radius of r. All right, we don't know, okay? But here's what we do know. We know that little is to big as little is to big. We know, let me get a good color for this. We know r is to 2 as h is to 4, right? Now, that's one way of writing it. You may have also said, let's see if we can erase a little bit. Whatever. So we can say, and my eraser's having some trouble here. So we could also say that 2 is to 4 as r is to h. All right, so both of these representations are great. All right, now what can we do from here? Well, what I'm going to do is I am actually going to take this representation here. This is equally good. You'll get the same answer. But I am going to do a little cross multiplying. Multiply h on both sides, multiply 4 on both sides. Or I could simplify 1 over 2. I get 1 over 2 equals r over h. And I would cross multiply. And what I would get is h equals 2r. Right? And that is what my next step is. All right, so I say, here we go. R over h is equal to 2 over 4, just as I said, which is equal to 1 over 2. Meters cancel. So that means cross multiplying, simplify here, 1 over 2, multiply the 2 over to the r, h times 1, 2r equals h, which means, check this out, this is really awesome. Not only do I know a relationship about r and h, but I also know a relationship about dr dt and dh dt. I can take the I can implicitly differentiate, let's just say that, left side and right side. 2 dr dt equals dh dt. Cool. So now we got a lot of information. So since we want to find dh dt, that is, it may have been lost in the mess of this problem. That's what our goal is. We want to find the rate at which the water level is rising when the water is 3 meters deep. Since we want to find dh dt and aren't given a value for r, dr dt is equal to 1/2 dh dt. So I'm solving for dr dt because I don't want to deal with it. I'm not given any information about it. I'm only given information about the height. I only want to find the height, all right? So we want to solve for dr dt. So we get dr dt equals 1/2 dh dt. That's taking this equation and solving for dr dt. And we also know that r equals 1/2 h. All right, so I solve for r here. I get 2r equals h, therefore r equals 1/2 h. So I've solved for r. I know nothing about r, but now I know it's equal to 1/2 h. I know nothing about dr dt, but now I know it's equal to 1/2 dh dt. So now I can take all those variables and cut it down a little bit by describing everything with an r in it, or a dr dt in it, with dh dt, and h. Cool. So now what I'm going to do in this next step is I'm going to replace all the dr dt's with 1/2 dh dt's. And I'm going to replace all the r's with 1/2 h's. That's what I'm going to do. Here comes the next step. There it is. So there was an r there, now there's a 1/2 h. There's an r there, now there's a 1/2 h. There was a dr dt here. Now there's a 1/2 dh dt. All right. So now we have everything in terms of h and dh dt. That's awesome. So we went from 5 total variables down to 3. This problem is now very accessible. Okay. So now we're going to substitute. We know our rate of change of volume with respect to time. We're adding 2 cubic meters per minute of water into our conical vessel. All right, and now we would substitute h here and simplify. Substitute h, all right, times 2/3 pi. Substitute h and simplify. All right, and now we have just one variable, dh dt. This is great. Now, I'm going to drop units to avoid confusion. There's a lot of stuff moving around, so I'm going to cut out units. All right, cool. So now we have simplified each of these parts of my sum on the right-hand side. And what I'm going to do is I'm going to say 3/4 pi plus 3/2 pi is equal to 9 over 4 times pi, or 9 pi over 4. All right. You feel free to pause the video right now if you got to get some writing done. I know that I'm saying a lot and showing you a lot. All right, I'll assume that we are good to move on. Now all we have to do is multiply both sides by the reciprocal of 9 pi over 4, which would yield us a rate of change, dh dt, of 8 over 9 pi. meters per minute. Right? Hope that floats your boat on that problem. Again, feel free to pause if you need some time to digest or to ask each other some questions about what's going on. Hopefully this all made sense. The big point here, is that with a related rates problem, if you can draw a good picture and label some stuff, you'll notice that sometimes with these geometry problems, if there's too many variables, then you can, if you need to find a certain dimension, take a derivative, and for what you can't find, use some similarity, some little is to big as little is to big, to help you out. That will give you the opportunity to do some substitution and to narrow your number of variables, which will make your problem possible. Not without a whole lot of scratch work, though. All right. So again, I'm going to show you this homework slide. There's a lot of details here. Again, these are on Google Classroom for your reference. But you can try a few more of these problems and you have the rest of class to do it. All right. Hope you enjoyed this video and have a great day.